Here we're going to look at torque and specifically the torque applied by static friction when we're talking about rolling. And we'll be applying Newton's laws so we can, solve more problems, all of that. That's kind of the broad scope of it. So I can't really do this demo right here, but if you imagine a yo-yo, right, basically, or a spool of thread or whatever you want, but you've got that inner radius and that outer radius, and you have string or thread or yarn or rope or something around the middle, and it won't slip, and it can either roll up or unroll on it, right? The gravitational potential energy as it rolls up increases, and the translational and kinetic energy decreases, right? And we think about mgh equals 1/2 mv squared, whatever it has at the beginning, plus 1/2 I omega squared, which is what it would have at the bottom. And so if you've ever seen a yo-yo trick, you know that it's sort of spinning and then you give it a little pull and it starts to catch and it rolls up. So if we think about the rotational rate right at the beginning, just as it starts to catch, that linear velocity, that angular velocity, which are linked by that v over little r relationship because that's where it's rolling up. The mass cancels out of this because it's in every term, but the radii don't, right? Because we have m capital R squared for the moment of inertia, and we have little r squared for the point where it's rolling up. So you have to be a little bit careful with that. And we saw that yesterday in class when we were looking at problems. If we talk about something like a cylinder rolling without slipping down a ramp, and whenever we say rolling, we really mean rolling without slipping, right? And if you want to find the acceleration of this object as it rolls down the ramp, which we often do, we can go about it in a couple of different ways. Well, really one primary way, right? What we are going to do is we are going to draw the object. We're going to pick our directions for acceleration. And the way we want to think about this is, since it's going to be rolling down the ramp and speeding up in the clockwise direction, I'll call clockwise angular acceleration positive alpha, and down the ramp positive a. And so they're consistent, right? We don't want counterclockwise positive while down the ramp is positive, because rotating clockwise would roll it down the ramp. Okay, we want those to be together. So the next thing we do is draw a free body diagram. And notice this is not one where it's all on a single point, right? This is our extended free body diagram. The force of gravity pulls right through the center of mass. The normal force is from the surface, right? That's how that's drawn. And the question we have to ask ourselves is, which way does friction point? Well, for that, we have a couple different ways to think about this. One is sort of the conceptual. If it's going to go this way and not skid, what does it need to do, right? If you were to sort of imagine, get rid of all the friction and drag this down the ramp, it would slide down. But if it's going to roll, then you need something to cause it to roll in that direction, right? That's the idea there. And then the signs of alpha and a must agree. So one of them is more an analytical write out equations way, and one of them is conceptual. But either way, we have force of static friction up the ramp. And the reason for that is that we don't have any forces on here that are applying torques until we get the friction. And so we need a friction that will cause an acceleration in the clockwise direction. We already have forces that will cause it to accelerate down the ramp. That's just, a thing sliding down a ramp problem. So now we can apply Newton's second law. We got two equations. Net force in the x along the ramp is ma. In this case, the forces involved are mg sine theta, the component of gravity force of gravity along the ramp, and static friction, negative in that case. And then net torque is I alpha. Force of static friction times the radius equals I alpha. Now, there's a couple of interesting things here, right? If this were just an object sliding down a frictionless ramp, the force of static friction term, right, wouldn't exist. And we would just have mg sine theta equals ma, and the acceleration would be g sine theta. But now we are going to get an acceleration that is smaller than that because we're subtracting force of static friction, which should make sense, right? We've talked about this a little bit, but if the static friction is up the ramp, it should slow down the rate of acceleration. But what is that friction doing? Well, it's actually causing it to rotate as it shows up in the net torque equation. So that's kind of what we're dealing with here. All right. Those are our two equations as we see them. So then we want to solve the simultaneous equations. We have three unknowns, but really it ends up being two because we have a third equation that lets us substitute either A or alpha. And then we can think about the static friction. Now, static friction is unknown, even if we happen to know the coefficient, right? The amount of static friction depends on these two equations, not on the normal force and the coefficient, because we don't know that this is max static friction. If we were doing something where you said we're trying to find it at the max, we might, but that's not what we have here. So we can go a little bit further. We'll change this one into A for linear acceleration, because the original question asked us about the linear acceleration of the center of mass. So we do that substitution. And then once we can cancel out some of those pieces, we can put the static friction, which is now 1/2 ma, in there. And now the m's will cancel out, and we can rearrange this and solve for A is 2/3 g sine theta. So the big deal here, and hopefully conceptually makes sense, is because friction is up the ramp and causes it to, and the purpose of that static friction is to cause rotation, what we've done is we've actually slowed down the translational acceleration, because some of that work, some of that energy goes into rotating instead of translating. And so hopefully that makes sense, right? A should be less than g sine theta. So we're going to predict the time t that it takes to go down. Well, now that we know the acceleration and it's constant for this problem, we can figure out the dimensions of our ramp. We can find out how long it takes to go down the ramp, like that. And we could test that, right? We could test this with a stopwatch or something like that if we were doing this as a demo in class. So what is the key idea here? Well, the key idea is that static friction applies a force and a torque. It can't do one or the other. Well, some forces could do one or the other, right? The normal force and the force of gravity only apply forces, no torques, because they're acting through the center of mass, whereas the friction applies a force and a torque. So here's what we do when we're talking about rolling objects. And we started with this in class the other day, and now we're going to kind of formalize it. We pick consistent directions for A and alpha. We draw the free body diagram, and this needs to be an extended free body diagram so we can see where the friction is acting. And that's the big kind of thinking part here. What is happening? If we know it's accelerating down a ramp, we know that the alpha and the A both need to have a change in a particular direction, and we can figure out which way static friction needs to go. And there's a couple different ways to think about this, right? Which direction gives me the correct A and alpha? Which direction prevents it from skidding? Another way to think about this is if you think about what would happen without friction, and then what is happening, the friction is the cause of that difference. Then we apply Newton's laws, both net force equals ma and net torque equals I alpha. And then you solve your simultaneous equations. So there is actually kind of a third equation in there, right, which is the relationship between A and alpha, which you need to be a little bit careful about, but that's also in that system of equations. So on pages 32 and 33, there's a couple of pages called The Role of Static Friction in Rolling. It's kind of fun. But when we do this, and we're going to be working on this in class because these are important, you're going to read through the instructions and draw the free body diagram and write the net force and net torque equations. And the big thing we really want to focus on is figuring out how static friction acts. That's the role of static friction. What does the static friction do? Which way does it point? Okay. The key things is that, again, alpha and A must agree with the way that they're working, and the static friction is there to prevent skidding. So I'm going to go through the first three cases. And then you'll have lots of time to work on the rest of them. So rolling at a constant velocity on a level surface. Well, if there were an acceleration, we would say clockwise and to the right are our positives. But constant velocity means acceleration is zero, which means alpha has to be zero, right? And the normal force is up. The force of gravity is down. We know that. And if we write out net force equals ma equals zero, and net torque equals I alpha equals zero, whatever forces or torques there are have to add up to zero. Well, right now, we don't have a push, so we don't have an applied force. So in the x direction, there do not need to be any forces to move at a constant velocity. And if there's no net force, right, acceleration of zero, then there doesn't need to be a net torque to cause an angular acceleration either. Number two, we are pulling on it from the center of mass somehow. At the hub, at the axle. And this is kind of like the back wheel of your, the front wheel of your bike, right, which doesn't have any power driven to it, or the rear wheels of a front wheel drive car, that kind of thing. We're just pulling it along with the cart. So again, we're going to do the same convention. We're moving forward. So if it's positive alpha, positive A would be that way. And we know that there's a normal force and a force of gravity. And we're going to say, well, the friction has to be backwards. Why? Well, if it wasn't, if there were no friction, it would just slide along. But it is rotating. It has to rotate clockwise and get faster clockwise. So we need a clockwise torque. Net force equals Fa minus Fs equals Ma. Net torque equals FSR. It's the only force providing a torque. So we have to have it there on that one. Last one here. Speeding up on a level surface due to a torque applied by an axle. This is like the front wheel of a car that's being driven, or the back wheel of your bicycle where the chain is pulling it around. You're applying a torque through those gears, but you're not pulling on it. And so in this case, we need to think about the right-hand rule. If it's going that way, the torque is sort of in, and it would be causing a torque to go in the positive clockwise direction, which we're going to call positive, right? So normal force, force of gravity, force of static friction. Force of static friction equals Ma, right? It's accelerating to the right. There has to be a force. There isn't any other one. And so what we actually have is the net torque is that applied torque minus the torque due to friction to give us that. All right. If you were to pull an object like this, and this goes with that yo-yo example I did before, which way will the object move? Well, the net force is to the right, so it moves to the right. Which way would it skid? Well, the force of static friction acts to prevent skidding, and it would just slide along that way, but it's actually rolling, so the force of static friction has to be backwards to cause it to roll up. And you can write the net force and net torque equations and inequalities for that too. And we'll talk more about that kind of problem in class. All right, that's it.